Right triangles and special right triangles. In this video, we will be focusing on right triangles. Let's get started. A ladder is placed against a vertical wall of a building, with the bottom of the ladder on level ground 5 feet from the base of the building. The top of the ladder reaches 12 feet above the ground, and the question we have to answer is how long is the ladder? Now, whenever we have a contextual problem like this, it's a good idea to sketch out a picture. And when we sketch that picture, we realize that we are talking about a right triangle because the building and the ground are perpendicular, and we are looking for the length of the ladder, which can be called the hypotenuse of this right triangle. So hopefully you'll recall in a right triangle with leg lengths A and B and a hypotenuse C, A squared plus B squared is equal to C squared. So we can substitute in the values of A is 5 and B is 12 from this contextual problem. We can square these values, 5 squared being 25, 12 squared being 144. We're solving for C, but there's an addition problem to do. That's 169 is equal to C squared. I want to know what C is equal to, not C squared, so I need to take the square root of both sides of this equation, and I get that C is equal to the square root of 169. I can use my calculator and find that the square root of 169 is 13. So I get that C is equal to 13, but in a contextual problem like this, when the question asks, how long is the ladder? It's a good idea to bring that context back into your answer. The length of the ladder is 13 feet. Let's look at another example, another ladder problem. This time, we know the length of the ladder. It's 15 feet. And it says that it's placed against a vertical wall of a building with the bottom of the ladder standing on level ground 12 feet from the base of the building. So I can label the hypotenuse of my right triangle and the base. What I don't know is the height, right? So in A squared plus B squared equals C squared, one of the legs is unknown, and we'll be solving for that leg. Let's substitute 12 for A and 15 for C. Let's square 12 and we get 144. Let's square 15 and we get 225. So we're going to substitute or subtract actually 225 minus 144 to get B squared. And that is 81. So we will subtract 144 from both sides and get that B squared is equal to 81. And then what number when you square it is 81? Either you know that that's 9, or you can take the square root of 81. And the answer to this question we will write as a sentence using the context of the problem. The ladder reaches 9 feet up the wall. So now let's move on to another topic. And this time we will remember how to classify triangles as acute, obtuse, or right, but not using the angle measures, but instead using the side lengths. The converse, or the opposite of the Pythagorean theorem, can be used to prove that a triangle is a right triangle. Consider any triangle with side lengths A, B, and C, where C is the longest side. If A squared plus B squared equals C squared, then the triangle is a right triangle. We have 3 examples down at the bottom, and in one of these examples, if you had a triangle with side lengths 7, 24, and 25, this one would be a right triangle. So how do I know that? Well, we're going to compare A squared plus B squared to C squared. And when we do, we square these numbers and we get 49 plus 24 squared is 576. You can use a calculator. 25 squared is 625. When we add these two quantities together, we get 625 is equal to 625. So that happens when A squared plus B squared equals C squared. We know this is a right triangle. Now let's look at this first example. And envision a triangle with side lengths 7, 7, and 8. It almost seems like an equilateral triangle, doesn't it? So hopefully you can visualize that this feels like it's going to be an acute triangle. So if I were to sketch that out, and it's not going to be a perfect sketch, and I put 8 on the bottom and 7 like this, these three angles will probably be acute. But let's use this, that if a squared plus b squared is greater than c squared, then the triangle is acute. So let's compare 7 squared plus 7 squared to 8 squared. 7 squared plus 7 squared is 49 plus 49. These two numbers are almost 50 and 50. It's like about 100. 100 is definitely bigger than 64. So without even doing it exactly, I know that I do have the greater than situation, and I know that this is acute. Finally, let's look at an example where the three side lengths will form an obtuse triangle. And this time my base can be 7. And if 4 are the lengths of the other two sides, you can see that there's going to be an obtuse angle up there. So this one is definitely going to be obtuse. Now, we'll use this relationship that if a squared plus b squared is less than c squared, the triangle is obtuse. So we're going to take a look at 4 squared plus 4 squared and compare it to 7 squared. 16 plus 16 is 32. 32 is definitely less than 49. So this is an obtuse triangle that we're talking about. Now, the last thing we want to talk about in this particular video is Pythagorean triples. You might hear this phrase, and it's important that you know what we're talking about. Pythagorean triples are whole numbers that can represent the three side lengths of a right triangle. The most famous Pythagorean triple is the 3, 4, 5 right triangle. That's the most famous triple. And many carpenters use the 3, 4, 5 to test if whatever they're building definitely has this right angle in it, okay? So the reason why 3, 4, 5 qualifies as a Pythagorean triple, it's because 3 squared plus 4 squared is equal to 5 squared. 9 plus 16 is equal to 25. There are many other Pythagorean triples that are related to 3, 4, 5. So we could just double these side lengths. 6, 8, 10 is another common Pythagorean triple. We could also multiply these three numbers by 3 to get 9, 12, 15. That's another common triple. But there are other famous Pythagorean triples. One is the 5, 12, 13, also 8, 15, 17, 7, 24, 25 are just some of them. In all of these triples, a squared plus b squared will be equal to c squared.